Hello again, Professor Simmons here. I'd like to talk to you about solving Laplace's equation in spherical coordinates without azimuthal symmetry. In class, we did the solution assuming azimuthal symmetry. But in fact, we started with the general case. We looked at a spherical situation, and we did a separation of variables, and we solved for the radial solution and found that it involved powers of r. And we solved for the solutions for the azimuthal coordinate, the one that marches around the equator, and found that that looked like e to the I m phi, where m is one of the integration constants from the separation of variables. And then we looked at the polar angle solution, the one that for the angle that marches from the North Pole down to the South Pole, and that was this equation here, the associated Legendre equation. And we said to ourselves, that looks too complicated. Let's set this m here in the equation, that integration constant, equal to 0. That reduces the situation to one where every point on the equator looks the same. In that case, one is solving simply the Legendre differential equation, and we found that the solutions were the Legendre polynomials as a function of cosine theta, but we tended to use the symbol x as a shorthand for cosine theta, and so the solutions in that case for the polar angle were these PL of x, the Legendre functions. Now let's go back to the associated Legendre equation today, and we will keep the term with m. We are not assuming that everything looks the same at every point on the equator of our sphere. When we solve this differential equation, the solutions are the associated Legendre functions found here. That is, you start with a Legendre polynomial, you take some derivatives, and you multiply by this function here. You can check for yourself by plugging these associated Legendre functions back into the differential equation for the variable y, that these actually are solutions for the differential equation, and I invite you to do that. What I'd like to do now is go through a few notes about the associated Legendre functions that are similar and parallel to the ones that we talked about for the Legendre functions. First, if we note the form of the associated Legendre function here, we see that it implies that the integration constant m has to be no larger than the integration constant L. That's because the Legendre function, whose derivatives we are taking, is a polynomial in x of order L. That is, the highest order term in the polynomial is x to the L. So we can't take more than L derivatives of it and get anything sensible. So m has to be less than or equal to L. This is not the only way to calculate the associated Legendre functions, however. Remember that for the Legendre functions, we had a Rodriguez formula that let us start with a simple polynomial and take some derivatives of it as a way of calculating the Legendre function. Well, the same is true here. We start with this simple function here, take some derivatives, multiply by another function and a coefficient, and voila, we have the associated Legendre function. One of the cool things about the Rodriguez formula is it tells us that actually m could have a value smaller than 0. Look here, this function x squared minus 1 to the L has a highest term, x to the 2L. That means, yes, we could take 2L derivatives of it, and that's fine. M could be as large as L. But here we see that this formula would make sense even if m had a value smaller than 0. So in fact, the formula works for m between any value negative L all the way up to positive L. So the relationship between the L and m integration constants should remind you of the relationship between the spin and orbital angular momentum components in quantum mechanics. Now, remember that the Legendre functions form a complete orthogonal set of polynomials on the interval from -1 to 1. The same is true for the associated Legendre functions. Remember that This meant we could do an expansion, a series expansion of any function on that interval in terms of Legendre functions. We could do a Legendre series. Well, you could do an associated Legendre series in terms of these functions. To do the series, you do need a normalization condition that tells you about an overall coefficient size to use in the expansion. And once again, we get that normalization condition by multiplying an associated Legendre function by itself and integrating over the interval. The answer depends on both of the integration constants. Of course, because the polynomials are orthogonal to one another, we mean that in the sense that if you multiplied one associated Legendre function by a different one and integrated over the interval, the answer would be 0. That's the sense in which they are orthogonal to one another. That's everything I wanted to say about the associated Legendre functions in particular. On the next slide, we'll look at the whole form of the solution. So let's look at the full solution to Laplace's equation in spherical coordinates without azimuthal symmetry. That means not assuming m equals 0. So here's Laplace's equation, and after we've done our separation of variables, the full solution looks like this. We sum not only on the integration constant L, but for every given value of L, we sum over each associated value of the other integration constant m. Here's our radial solution, which looks very much as it did in the simpler case we studied in class. The only difference is that we are putting indices L and m on the a and b coefficients to remind ourselves that the coefficients could have different values for different values of m. We see here's the e to the m phi solutions to the azimuthal angle differential equation, and here are the associated Legendre functions for the polar angle, just as promised. Note that the full combination of the angular piece of the solution is proportional to the familiar spherical harmonic functions. Finally, we see that if you set m equals 0 and go back to an azimuthally symmetric case, the solution reduces to the simpler form that we saw in class, with only radial and polar angle components, and the polar angle components are now the simpler Legendre functions. That's all.